As we look at 3.2, we look at evaluating determinants using elementary row operations. So let's just review real quickly how we evaluate a basic 2x2 determinant. So if our determinant is 2, 1, 1, 3, to calculate the determinant, we multiply down this diagonal, multiply up that diagonal, and subtract. So this determinant would give us 5. Now let's compare that with a matrix or a determinant that's row equivalent with A. So to begin with, let's swap the first two rows. So let's say matrix B is the same as matrix A, except the first two rows have been swapped. Now let's take the determinant of that. We multiply down this diagonal minus up that diagonal, we get -5. So if we achieve one matrix from swapping rows from another, then the determinant of A will be the opposite of the determinant of B. Or you could say the determinant of B is the opposite of A. Either way you want to phrase that. So that was one of our elementary row operations. Another elementary row operations was adding a multiple of one row to another row. So let's suppose A is 1, 3, 2, 1. Then first of all, let's calculate the determinant of A. That's 1 minus 6, so -5. Now, let's take A. Let's get a matrix that's row equivalent to it by taking -2 times row 1 and adding it to row 2 to get our new row 2. So our new matrix has the same first row, but if we do -2 times this plus this one, we get 0. -2 times 3 is -6 plus 1 is -5. If we want the determinant of this is upper triangular, so we can multiply down the diagonal, and we get -5. So if we multiply one row by a scalar and add it to another row, then the determinant of those two matrices are the same. So if we swap rows, they're the opposite, but if we add a multiple of one row to another row, the determinants are the same. Now, so this is if we swap rows. The determinant, the first one is the same as the second one. We add a multiple of one row to another. So our other operation was to multiply a row by a scalar. So multiply a row by a scalar or by a number. So let's see, let's take 1, 2, 3, 1. So that determinant is 1 minus 6, so -5. And let's see what happens, just out of curiosity. Let's call that A. If our new first row is 3 times our original first row. So if we take the first row and triple it, see how that affects our determinant. So the determinant of B is 3 minus 18, so negative 15. So this was our original determinant. That's the determinant of A. The determinant of B, we got to be negative 15. So if we take A and multiply that matrix by 3, that first in one row, then 3 times that determinant will be equal to the determinant of the new one. Which, what may be more useful to say is that our original determinant, which is often what we're looking for, is 1/3 our new determinant. So if we want to know what A is, well, let's say multiply a row by, let's say, call it K. Then the determinant of A will be 1/K times our new determinant. So this turns out to be fairly useful because if we have a larger matrix that we want to evaluate, a larger determinant that we want to evaluate, instead of having to break it up into lots and lots of cofactors, we can break it into something that we put in row echelon, or we can make it upper triangular, and we can multiply down the diagonal to get our determinant. Now, if we have to do several operations to get from A to B, their determinants might not necessarily be the same, but by using these 3 properties, B would be something we could easily calculate the determinant of. We could use those properties to figure out what A is. So let's look at an example. Let's suppose we want to calculate the determinant of 1, 1, 1, 2, -1, 2, -2, 1, -2, -1. So let's row reduce this determinant so that it is upper triangular. So to get a 0 here, we need to do negative twice the first row plus the second row. That'll give us our new second row. To get this to be a 0, we want to do the opposite of the first row plus the third row to give us our new third row. And remember, if we're only adding a multiple of one row to the other, that doesn't change the value of our determinant. So our new determinant, our new matrix that we're taking the determinant of is 1, 1, 1. -2 plus 2 is 0. -2 minus 1 is -3. -2 minus 4 is -4. -1 plus 1 is 0. -1 minus 2 is -3. -1 minus 1 is -2. So we could get this to be a 1, but if we just want it to be upper triangular, let's go ahead and make this a 0. So if we do the opposite of row 2 plus row 3 to get our new row 3, we have 1, 1, 1, 0, -3, -4, 0. The opposite of this is the 3, minus 3 is 0. The opposite of this is a 4, minus 2 is 2. And if we want that determinant, it's upper triangular, so multiply down the diagonal. 1 times negative 3 times 2 is negative 6. So if we call our resulting matrix in here B, notice each of our elementary row operations, all of those were adding a multiple of one row to another. Add a multiple of one row to another, a multiple of one row to another. And we said that anytime we add a multiple of one row to another, that doesn't change the value of our determinant. So if we call our original matrix A, then that's the same value as what we got when we calculated B. And we could do the same thing about a column. Now earlier when we were looking at calculating determinants in the first section, we said we could expand across a column or across a row or down a column. We can do the same thing when we do elementary row operations. Now normally when we row reduce, we try to get zeros under the first number, some numbers over here, maybe a 1 here, 0 here, and so forth. But in order to calculate a determinant and make it easy, we don't necessarily have to have zeros here or have it diagonal. Remember, we could expand down this column and we would have this element times the cofactor crossing out row and column, which in this case would be that product. But if we had a number, let's say a 1 here, a number, zeros under here, numbers here, we can expand down this column and we only have one that we have to do, one expansion. So sometimes when we add columns together, it might be such that we get zeros here or zeros here and here, just depending, whatever is the easiest to achieve. So let's do another one. Let's take 3, 8, negative 7, 0, negative 5, 4, 6, 1, 6. And let's row reduce it. So let's get a 0 here. So let's do negative 2 times the first row plus the third row to get our new third row. So we have 3, 8, negative 7, 0, negative 5, 4. And if we do negative 2 times this, that's negative 6 plus 6 is 0. Negative 16 plus 1 is negative 15. Negative 2 times this, that's 14 plus 6 is 20. If we want a 0 here, we need to multiply this times negative 3. Or, we don't necessarily have to, but we could reduce this. Both of these have a 5 in common. We can multiply that by a 1/5 divided by 5. But let's just go ahead and get a 0 here. So let's do negative 3 times row 2 plus row 3 and see if that gives us our new row 3. So 3, 8, negative 7, 0, negative 5, 4. Negative 3 times 0 plus 0 is 0. Negative 5 times negative 3 is 15 minus 15. 4 times negative 3, that's negative 12 plus 20 is 8. If we take this determinant, it's diagonal. upper triangular, so we can multiply right down the diagonal. 3 times negative 5 times 8, that's negative 15 times 8. And what's that, negative 120? And since the only elementary operations that we did were to add a multiple of one row to another, we didn't change the value of our original determinant. So we can say our original determinant is equal to negative 120, even though we didn't directly calculate that determinant by properties of determinants. We calculated an easier one. We know how it's related to this one. And in this case, they have the same value. Now, one thing that's mentioned, let's observe this determinant. Notice that this row is a multiple of this row. So if we were to take negative 2 times the first row, add it to the second row to get our new second row, we would have that still the same. Negative 2 plus 2 is 0. Negative 2 times 2 is negative 4, plus 4 is 0. And when we calculate this determinant, we get 0 minus 0, which is 0. This is the same value as our original determinant because we just did a multiple of one row plus another one. So this determinant is also 0. So one thing, anytime one row is a multiple of another row, or if one column is a multiple of another column, your determinant will always be 0. That has to do with the fact that when we row reduce that, we have a 0 row. Anytime we have a 0 row or a 0 column, then we'll have a 0 for our determinant. Notice if we have a 0 column, we have 0 minus 0. So if you can row reduce a matrix or column reduce a matrix to get a 0 row or a 0 column, that determinant will always be 0. Whether it be 2 by 2, 3 by 3, or whatever. Notice if we have all zeros on that first row, or on any row, if we expand across this, it's 0 times our 1, 1 cofactor, 0 times our 1, 2 cofactor, 0 times our 1, 3 cofactor. So for each of those expansions, we get 0. So the value of that determinant is 0. So anytime you can row reduce or column reduce a determinant to get a 0 row or a 0 column, then 0 is the resulting determinant. And we'll mention later more consequences of that, but that's enough on that for now. Now, just a little comparison. In the book, it lists how many calculations it would take to calculate various determinants. And if we have a 3 by 3 determinant, and we want to calculate it using cofactor expansion, then we have to do 5 additions, possibly 9 multiplications. If we do it by row reduction, we could possibly have to do 5 additions, 10 multiplications. But as we get to larger and larger, it becomes much more efficient to use row reduction instead of cofactor expansion. Notice a 5 by 5, we might have to add 119 row combinations. We could possibly have to multiply by a constant 205 times, whereby doing row reduction, it would only take 30 additions, 45 multiplications. Because think about it, if you have a 5 by 5, you're going to have to 5 times do a 4 by 4, and then for each 4 by 4, you're going to have to do 4 3 by 3s, and then for each 3 by 3, you're going to have to do 3 2 by 2. So you can see, even with the 5 by 5, you can get into having to do lots and lots and lots of cofactor expansions because they're nested. Where with row reduction, if you have 5 rows, 5 columns, you'll do at most 4 combinations of rows to get zeros here, 3 combinations to get zeros here, 2 combinations to get zeros here, get a 0 here. So it wouldn't take you tons and tons of steps to get that. So then you could multiply down the diagonal once you got zeros here, and you could get your determinant. So the book mentions that since these are nested for cofactor expansions, that they grow for an n by n matrix, they grow like n factorial. And actually the way they came up with these numbers is they took, if this is n, they took n factorial and subtracted 1 from it. This is 5 factorial minus 1. You don't have to understand exactly why that is, but let's suppose we had a system with 30 equations, 30 unknowns. An example of that might be some electrical system. So 30 factorial, roughly 30 factorial minus 1, that's something on the level of 2.65 times 10 to the 32nd power. Now, just to grasp how large that number is, if you had a computer that could do 1 trillion operations per second, or 1 trillion operations per second, it would take over 1 trillion years to calculate one of those. So that's a lot of calculations. That's a long time. Where on the other hand, if you had a 30 by 30 and you put it in upper triangular form by doing row reduction, that is something you could do by hand. And I mean, it would take you a little while, but you could do in a day easily, not faster. A computer could do it in a few seconds. So just to kind of get a grasp of why doing things by row reduction is so much faster, because as you get past a 4 by 4 or even past a 3 by 3 determinant, it takes lots and lots of cofactor expansions to get to finally having lots of 2 by 2 determinants that you can calculate directly.